First of all, my name is Andrea Poet. I'm Program and Public Relations Director, or Associate, for Chicago Council on Science and Technology. First of all, would like to welcome all of you in attendance, those joining us via live stream this evening, and would like to extend a special welcome to the Counselor on Environment and Energy from the German Embassy. Thank you all for coming. For those of you who are unfamiliar with Chicago Council on Science and Technology, we are a non-profit, membership-based organization. We bring together universities, national laboratories, museums, and industry. We pull research and researchers out of the labs and bring them directly to you. We like to focus on the Chicagoland region, which is rich with science and technology, and we like to showcase the importance of this work to the economy and the region as a whole. Today is our 85th program that we've produced in 7 years. We could not have made it this far without our wonderful members, partners, sponsors, and advocates. Little plug for membership. If you liked what you hear tonight, I highly encourage you to join our organization as a member. You can visit Peter in the lobby afterwards. He'll be waiting for you. What you get is a chance to attend most of our programs for free or at a highly discounted rate. If you join today, the price you paid to get in tonight will be applied towards your first year of membership, so it's quite a deal. We also would like to announce an exciting new venture. Our Climate and Energy series, which tonight's program is a part of, has gotten a wonderful kickoff for our spring season. We've gotten a very generous donation from two of our supporters, Joel Friedman and Roger Nelson. So we'll be able to have many more program likes tonight, starting in the spring. Just please check with our social media sites and newsletter for program announcements for those upcoming programs. As far as our presenter tonight, Dr. George Crabtree, this is his second program with us. We are thrilled to have him back with us. I personally met Dr. Crabtree as a student in his summer institute on sustainability and energy a few years ago. The Institute brings students from across the country and across disciplines to learn about the environment, climate change, energy, and the problems facing the world in the immediate future and beyond. Like C2ST, Dr. Crabtree brings the best experts from different fields to fully immerse students in the issues, and then gives students projects based on real-world problems, and you have 2 weeks to solve them. Judges are brought in from industry, and the competition is fierce. There are prizes awarded. It is a DOE-sponsored institute that it's grown over every year it's existed, and this is something Dr. Crabtree does in his spare time, which leads me to his real CV. He is director of the Joint Center for Energy Storage and Research, also known as JCESR, senior scientist and distinguished fellow in the Materials Science Division at Argonne National Laboratory. Dr. Crabtree is distinguished professor of physics, electrical, and mechanical engineering at University of Illinois at Chicago, where he's also director of the Energy Institute as well as the Summer Institute on Sustainability and Energy. He's won numerous awards for his research. He's published more than 400 papers in leading scientific journals, has collected over 16,000 career citations, and has given over 100 invited talks at national and international scientific conferences. His research interests include next-generation battery materials, sustainable energy, materials science, nanoscale superconductors and magnets, vortex matter and superconductors, and highly correlated electrons and metals. He's testified before the U.S. Congress on the hydrogen economy and on meeting sustainable energy challenges. Please join me in welcoming Dr. Crabtree.
Well, thank you, Andrea. That was a wonderful introduction, probably more than I deserve. And thanks also for mentioning SIZE, our Summer Institute. I'll say a little bit more about that at the end of the talk. And I have to say, it's one of the most satisfying experiences that I've had as an educator and as maybe a stimulator of critical thinking. And it's great to see all these wonderful graduate students from around the country stretching their minds. And that's the experience that we had last August and we'll repeat again next year. So I want to, tonight, encourage you, I guess that's the right word, to think a little bit unusually, out of the box. And I want to talk, so the title, The Price of Doing Nothing, the World's Energy Future. I want to talk about energy, the future of energy, in a way that you may not have heard before. So I want to take a 50-year outlook not the usual 25-year outlook, which is typical when you try to extrapolate energy into the future. But I want to take a 50-year outlook, and I'll tell you why in one of the early slides. And I want to think in a way that we don't usually think. So typically when we extrapolate the future, we go 25 years. We assume that it's just like the present, but some prices will change because some technologies will get less expensive, and there may be some climate issues or other issues, and we think of the future as the present extrapolated. And in particular, we usually assume, because we're conservative and we don't want to appear to be too optimistic, we assume that there won't be any breakthroughs. So I want to take the other point of view. I want to say, let's go 50 years. That's really the time it takes to change the energy system. And let's assume that in 50 years, there will be breakthroughs. So let's try to factor that in. And instead of being passive about projecting the future, it's just like the present, only incrementally different, let's be proactive. Let's ask, in 50 years, what kind of society would we like to have? And then what kind of energy and other science breakthroughs relating to energy do we need in order to enable that society? So this is a way of thinking that is not at all normal. But I would like to submit that that's how you have to think if you want to, in a sense, determine your future rather than just follow some path of least resistance, and that it takes a lot of, let's say, education and critical thinking about energy to decide what are the top priorities for the society that we'd like to have in 50 years. So I've just more or less said what's on this slide. Oh, I should acknowledge my co-authors, Elizabeth Koch and Thomas Elan at University of Illinois at Chicago, who helped put this talk and paper, which we hope will be published before the end of the year, in print. So let's start. And let's start with an image of energy. Almost everything that society does depends on energy, and I've shown some of the things here. Transportation, in this case an airplane. Agriculture, which requires gasoline and harvesting and planting and fertilizer, all of which depend on energy. Cities, such as the skyscraper you see there, which costs an enormous amount to build and maintain, but it gives us living space, it gives us commercial space, it gives us business offices, which are all very useful and which we like to have in cities because they're conveniently located. The next image is health. So almost everybody has had an MRI that uses energy and some very clever science in an innovative way to look at what's wrong with your body without ever touching it. It's really quite an advance. And of course, communication, and you see the guy there that looks like many of us. So every picture you see here is energy transformed into a different form. And in fact, everything that society does requires energy. If energy is cheap and abundant, society has big aspirations and big opportunities. If energy is expensive and scarce, it's just the other way around. Hard to make progress, hard to have innovation, and hard to make life better. So in a way, energy is the basic element of life, and it determines both our aspirations and our limitations. So here's the slide that tells about 50 years. This is a slide that came from a paper by Stephen Chu and Arun Majumdar. Stephen Chu was our Secretary of Energy for the last 4 years, so he probably knows what he's talking about. And it shows, since 1850, the percentage of various fuels that have given us our energy supply. And you see back in the very early days, mostly wood. Then along came coal, and it turns out that's better than wood, has a lot more energy in it. It's pretty easy to mine out of the ground. Oil in the 1950s, after World War II, we decided to drive. We built the interstate highways and decided every family should have one or more cars. And so suddenly oil, which is the source of gasoline, grew as an energy supply. More recently, natural gas. This only goes up to the year 2000, so it doesn't include the shale gas, which is now cheap and abundant and really quite potentially a revolution in the way we deal with energy. The little yellow thing up there is nuclear, and it started to grow back in the 60s when we first deployed it, and in the 70s encountered some resistance because of accidents, so Chernobyl and 3 Mile Island and recently Fukushima. It's been pretty stagnant since then, but it's a technology that we know how to do, and if we wished, if we knew how to do it safely, we could deploy even further. If you have a very good eye, you can look at the top right-hand part of that graph and see a tiny sliver that's sort of bluish. Those are the renewables. So they haven't really started yet to give us much energy. But if you look at the other energy sources there, you see that it takes about 50 years to change the energy system. So going from wood to coal, coal to oil, you can see gas growing on a 50-year time scale. That's the time it takes to change the world and the way we use energy. So there's a couple of lessons from that. One is that the world we get in 50 years depends on the energy decisions we make now, because it takes that long for the system to change. That's once you know that you can do it. So if you're going to be very strategic, and this is the point I was referring to before, then you ought to be asking, what kind of world do we want in 50 years, and what kind of energy breakthroughs do we need now to enable it? So that's the 50-year time scale. So I mentioned this before, but just to reinforce, the conventional way of sort of predicting the future is to take today's technologies and extrapolate what you think will change economically and perhaps regulation and other things that affect how we use energy. Assume there won't be any breakthroughs because you don't want to assume something that may not happen. And then you get the bottom line there of that first box. The energy future is a continuous extension of the present. So the point of view that I would like to give, and I mentioned this before, is proactive. So define the global society you want in 50 years. Identify the strategic energy outcomes that you need to achieve that society. And then target strategically the R&D that needs to be done to get the breakthroughs that will enable that energy society of the future. So the bottom box there, the yellow box, 50 years is long enough for energy R&D to produce breakthroughs, and we can actually steer the energy society nexus by controlling this. So the question you now have to ask is, what kind of society do you want in 50 years? So I've chosen some things here, and you may disagree, but and that's fine, we should have a discussion. But most of the things that I've chosen have, I think, are things that many people in the world at least would say are good choices. First one, rapid growth of the developing countries. So they're going to grow anyway. It's certainly their aspiration to grow. And if you look at Asia, particularly China, you can see how fast that growth can happen. It's probably going to happen whether we developed countries sanction it or not. And in a way, it's something that you can understand, right? Everyone wants to aspires to a better life, and that means economic development. So that's the first bullet. Second one, also steady growth of developed economies. So we know what happens from the Great Recession of 2008 on when you don't have economic growth. Life is tough. So we're unhappy people in a sense. We're starting to recover from that recession, but not as fast as we would like. It has many long-term impacts, and it just makes it difficult to go forward. So you need, even in developed countries, you need economic growth. That's my second point. Third point, aggressive pursuit of discovery, science, and innovation. Why? Because that's the way you move forward. It's the discovery science and ultimately, or eventually, the innovation that brings you new technologies, like your cell phone. But you can name lots of other things, and shale gas is a good example. If you go back 10 years, no one would have said, oh, there's going to be abundant and cheap natural gas because of fracking. No, not at all. However, we now have it. That's an example of innovation. So that's a very important bullet. Rapid deployment of innovative technologies. Once you know about them, you'd like to get them out. Lively communication of trade and exchange of people and ideas across national and regional boundaries. So that means, for example, the developing countries should participate in the intellectual process of discovery and of innovation and developing new technologies. In a way, they will anyway, but the whole world benefits from that because you have more people, more resources devoted to moving forward. Finally, globalization of opportunity and participation in scientific technology and economic, social, and cultural advances. We should all benefit from that. So to sum it up, again, the yellow box, a vibrant, interactive, inclusive, and rapidly advancing global society. So that's my sense of what we should have in 50 years. Then how do you get there? What energy outcomes do you need to achieve this kind of a global society? Well, I have 3 of them here. So one is energy security, and that's something that we don't have at the moment. Oil is the best example of that. So before 2008, oil at its peak was costing $140 a barrel, and the Great Recession came along, and within a year it was $40 a barrel. Pretty hard to predict. Go back to 2002, and the price of oil was $28 a barrel and had been at that level or lower for decades. So you couldn't have predicted that, any of those swings. And when you can't predict, you don't make long-range plans. So if you only can predict 6 months or even a shorter time, then that's what you assume you have. If you knew that the price of energy would slowly rise a few % per year, you'd make plans and you would phase out certain technologies and bring other ones in. If you have no idea what the price of energy is going to be, you just don't do that. You don't want to take a chance. So it's very important to have energy security, and I've listed the attributes there. Should be adequate supply, should be affordable, so not too expensive, should be sustainable. We can use it for a long time, unlike, for example, fossil fuels, which by definition are finite, and at some point will reach a limit, and should be predictable. And that's what I was explaining earlier, how important that predictability is. And we don't have that predictability now. Second point, stable climate. Why? Because if climate change occurs, and let's take, you don't have to take the worst case scenario, but let's just say it continues to become more extreme, it's going to be expensive. You have to adapt to that climate change, and it affects all the populations of the world. So especially the seacoast populations. It could change the agricultural patterns, the way we grow our food. It could certainly change the patterns of trade. And if it goes far enough, it gets to be very expensive. So why does that matter? And this is a very important point. The world, as an economic unit, only has a certain amount of, call it, disposable income to spend on going forward. So you have to feed everybody, you have to house everybody, you have to have some minimum standard of public health for everyone. And once you provide that, what's left over is what you can use to move forward with. If there's climate change, serious climate change, that leftover amount, the dispensable income, is going to be devoted to accommodating climate change, and we'd rather use it for something else. So I believe that a stable climate is absolutely essential if we're going to move forward scientifically and economically. And the third point, economic development and growth, that's sort of the engine of everything. So the developing countries need that if they're going to achieve the lifestyle of the developed countries now. The developed countries need it simply to keep the engine going. So there has to be an element of growth, economic growth, and that requires energy, right? So that requires abundant and inexpensive energy. So these are the 3 outcomes that at least I've put on the slide. You may have different outcomes, but let's follow this line of argument and see where it goes. So what are the energy science outcomes that we need? What are the breakthroughs that we need for the next 50 years? So I have quite a few of them here, but I've divided them into the ones that are on the road. To me, that's code for we've started it and it looks good, let's keep doing it. It's a very positive development. And I have only one bullet there, replace fossil with wind and solar electricity. So we'll talk about that. And then another category, on the road but not yet sustainable. And I have two bullets there. First one is replace coal and gas electricity with high-performance nuclear electricity. And please, I didn't say it, but I have it there. The first adjective is safe. It has to be safe, and the public does not believe that it's now safe, and it probably may not be safe. So we have to do something different to achieve that safety. But if we could do that, that's something you can deploy now. We understand the technology. It could be deployed on a wider scale. Second bullet, replace coal and oil with safe, abundant, and inexpensive shale gas. So shale gas is, in a sense, a revolution. There's a lot of it. The price is way down. It has the potential to reduce the carbon dioxide emissions from coal by something like a factor of 2, and be an energy source for the next, let's say, many decades. So we'll talk about that. And then some things that are not yet on the road. So we haven't even started them. These are a little bit farther out of the box. Hard to do, but with breakthroughs we can do. So mitigate carbon emissions by mineralizing carbon dioxide to rocks. So the solution you hear, if you want to take carbon dioxide, put it somewhere other than the atmosphere, the solution you hear most often is, let's put it underground, we'll sequester it. And I'm going to suggest in this talk that instead it be mineralized, turned into carbonate rocks, which you can store anywhere, or build limestone, calcium carbonate, is a carbonate rock, which you can build buildings out of, or do lots of useful things with. So that's hard to do, but with breakthroughs we might be able to do it. Develop electricity storage for cars in the grid, and that is the vision of JCESR that Andrea was talking about in her introduction. We'll talk about that a little bit. And the last one, the third bullet there, is a tough one intellectually, but within reach, will make chemical fuel a sustainable energy carrier. So not only will it not emit carbon dioxide, or it will not increase the carbon dioxide in the atmosphere, but will make it last a long time as well. And we'll do that by recycling the carbon dioxide back to fuel. So it's an aggressive agenda. We have 50 years to do it. That's the time scale we're looking at. And I would submit that these are things that we ought to be trying to do, that is, give them priority. So let's start with wind and solar electricity. So we want to replace the coal plants with wind and solar. Those are the images there on the left. Here's a graph of the growth of wind and solar since 1980 up to 2011. So not 2012, but 2011. And you can see wind has taken off. It's the cheapest one of the two. We know how to do it. It's pretty standard technology. Things go around. You put a generator on it and so on. So that's something that can be deployed, and in fact has been deployed pretty widely. So solar is behind, but if you look at solar there, you see it has a very sharp slope now. And in the last 3 years, the price of solar photovoltaics has come down by about a factor of 2. That's a huge incentive to put more out there. And the predictions are that its slope will grow going forward and perhaps achieve at least the same slope that wind has achieved. So can we do this? Well, you see 60 gigawatts installed for wind and add another 10 maybe for solar, so 70. How much of our electricity is that? Well, wind does not blow all the time. In fact, in every month, there's at least one day that is calm for almost every wind farm. The sun shines only during the day, and clouds pass over during the day. So you don't get the full 70 gigawatts that you'd expect. You get something like 20% of that on the average, and it's different for wind and solar. But that gives you maybe 17 gigawatts. The average U.S. use, the second line there on the graph, is 450 gigawatts. So that's averaged over winter, summer, night, day. If you just produced 450 gigawatts as a constant all the time, that's the electricity that we need. So it's around 3.5 or 4%. But it's growing at each one of those, wind and solar, are growing at 30% a year. That's hard to maintain over the long time. Now we don't have a lot of wind and solar, so it's in a sense easy to maintain. But let's assume that you have 15% growth every year. Then by 2030, you would have 40% wind and solar. So these are on track, potentially, to meet the goals that many states have, which is 20% by 2020. So that looks promising. You could do that. We just simply need to overcome the science obstacles. So make, in the case of solar, make it more efficient, make it even cheaper. And in the case of wind, we need to simply deploy more, and the price will come down because of the learning curve.
Don't you also need storage and
yes.
balance of the grid?
Absolutely, and I'm going to come to that. So if your wind farm is calm for a day and it's 30% of your electricity, you got to get it from somewhere. And I'll answer that. If I don't answer it, ask me again. Another question? No. So what about nuclear? So the things that are on the road but not sustainable. So we've had nuclear energy since the 60s. That's when we first started to deploy it. And it started to grow rather quickly in the 60s until we encountered some accidents. 3 Mile Island, Chernobyl, and recently Fukushima. We know how to do it. If we decided to do it, we could just deploy it on a much larger scale. We don't do that because we don't think it's safe. So there's some challenges you have to overcome. Safety, I think, is the biggest one. I don't really think nuclear is going to grow at all until not just the experts, but the public believe that it's safe. So that's a challenge. It's 1960s technology. We can do a lot better. So if you were going to start now, you wouldn't do it the same way that you did in the 60s. And you have a challenge, the spent fuel. Don't know what to do with it. It's probably going to last hundreds of thousands of years or thousands of years, depending on how you process it, and we don't really know what to do with that. It's a problem that is not solved yet. So those are the challenges. Let me start with 1960s technology. So that's what we have now. It's about 35% efficient. That means 35% of the heat from the fission of the nuclei ends up as electricity. You could make that 50%. All you have to do is raise the temperature of operation. That's the Carnot efficiency. So you could get 50% out of that, but you would need materials that can withstand those higher temperatures and the higher neutron fluxes. That's how you raise the temperature. You have more fission per second, and that means you have more neutrons. So it's a materials problem. But there are materials, here's one of them, it's a copper niobium sort of layered material, which it turns out is capable of withstanding those neutron fluxes and also withstanding the temperatures. So there's plenty of opportunity to make the materials that you need. Again, it's a science question. It's a discovery and an innovation challenge. What do you do with the spent fuel? Well, the current idea is to stick it underground somewhere, not unlike carbon dioxide, where you hope it will be stable for thousands or tens of thousands or hundreds of thousands of years. Why is that such a challenge? Because society itself or civilization itself is only 10,000 years old, and we don't know if we can keep things safe for that long. There's never been an example to show that you can do it. So that's a challenge. And then with that spent fuel, it's usually put underground or taken out of the reactor with only 4% of the uranium fuel is used. So most of it is not used. If you reprocessed that fuel, got the usable uranium and plutonium and other fissionable ions out, you would, number one, reduce the amount that you put to storage. That helps to the storage problem. And you could reuse that fuel and get more energy out of it. So these are opportunities that we can shoot for. And they are, I would submit, science opportunities. You have to make some science discoveries for the materials, test them, make sure that and improve them, for the spent fuel, for the reprocessing, and most importantly, for the safety of the reactor. But that's a science challenge. How about shale gas? So as I mentioned, if you go back 10 years, nobody would have predicted that we would have shale gas in such abundance and at such low prices as we have now. Yes. Yeah. Yes.
We do have the new design. We are aware.
With-
81,000.
Yes. And it's certainly an improvement over what we had.
Yeah.
Right.
Towards this state. It's very important actually make it very efficient.
Well, there's that, and there's some ideas that aren't yet implemented, things like small modular reactors and so on. And I think, just since we're on that point, that it's not enough to put on the table, here's a safer reactor. I think the challenge is to convince the public in language that they understand that indeed it's safe. And I haven't seen a lot of progress in that department. The experts are arguing back and forth, but if you don't have the public, it's not going to happen. That's my feeling. Yes, exactly. Yes, and people have to think about this problem in a very intelligent way and come to a conclusion. That's exactly right. Yeah. So back to shale gas. Here's the prices you see up here in the middle box. Between 2005 and 2008, the peak was $12 for a million BTUs. The non-peak, off-peak, was $8, and since January of 2012, it's been between $2 and $4. Really a dramatic reduction in price. And now the energy you can get from shale gas costs you much less than the energy you can get from coal or gasoline. So you may ask, why don't we use this shale gas, replace coal for generating electricity? And that's happening, actually, thanks to the EPA, in part, the regulations that are now proposed but not yet in force on coal plants. And just simply thanks to the low price and the abundance. So people are building very efficient, I should point out, combined cycle natural gas turbines that are about 60% efficient. It's really quite remarkable. So there's a lot of advantage to using that gas, probably, and actually, certainly, as a transition fuel, because you can do better than that. You can, as I'll tell at the end, maybe have sustainable chemical fuel. But for the moment, this looks pretty good. It's a potential game changer. And just to show you, a very conservative organization like the Energy Information Administration in the US, it's part of DOE, predicts that this is the future of shale gas, going out 25 years, which is the typical prediction. 23% in 2010, it'll be nearly 50% by 2035, according to this prediction. And this assumes no breakthrough. So this is just present technology and no science operating. So it's a big thing. The upper right graph shows where some of the shale gas deposits are located around the world, and it's pretty uniform. The gray areas, they're gray because we don't know if there's any shale gas there, so it doesn't mean there isn't any, we just don't know. But in the white areas, you see that it's pretty common. So unlike oil, it's much more generally available than oil is.
Can I make one comment?
Yes.
On the price you have there.
Yes.
According to the makers of shale gas, it's about $5 per million.
So this slide is a little bit old.
Yes.
Absolutely.
Plus you have the pressures from wind and solar in terms of their capital costs. If that gets $2 million, they've got
Absolutely. And
so all that's nice, but the price will go up.
well, and actually the price has already gone up because it's too abundant. So if you look back a year or two when those prices were much, yeah. And drillers have now gone, instead of drilling for shale gas, they drill for shale oil. And that's one reason why the Bakken shale in the Dakotas is producing so much and not so much. So there's certainly a supply and demand fluctuation that will happen. Yeah. Good point.
What about George, that leakage from shale gas to the atmosphere?
That's the next slide. Absolutely. So this is the positive side. Here's the negative side. How do you drill for, how do you do hydraulic fracturing? You drill a well down, maybe pretty deep, so thousands of meters, till you find the shale seam. The shale seam is usually not very thick. And then you turn the horizontal drilling, and this is what we've learned to do so well in the last 5 years. You drill horizontally, keeping the well bore always in the shale seam, so you don't go out of it. You drill this way, and of course you're also going to drill this way, this way, this way, and 360 degrees around to access as much of that shale seam as you can. And then you put a hole in the well bore at its end and pump high-pressure water there. The high-pressure water, the pressure exceeds the yield strength of the shale and fractures it. And then when you're done with that, you put a hole, you do the hole explosively in the well bore a little farther back and then a little farther back and so on. You do a sequence of these fractures. So the fracture goes through the shale seam. You don't want it to go outside the shale seam, right? Because if it goes outside on the top, that leaks the methane gas into that porous geologic formation. Who knows where it will go. It also leaks the water that you've used for fracking, which is not at all pleasant, even when you put it in the well at the top, but it gets much worse when it gets down to the shale seam. There's lots of toxic things down there that contaminate the water, and you don't want that floating around in the geologic formations either. So there's a challenge here. Oh, and there's another point from the producer side. So those are things that we consumers don't like. But there's a point from the producer side that you only get, over the life of the well, maybe about 15% of the shale gas which is there. So if you're a producer, you'd say, why should I take 15%? I'd rather have 30% or 50% or more. Yes. It declines faster than the ordinary natural gas well, much faster. So here's my thesis, that you can solve both of these problems by science. You can learn to understand where the fractures go in the shale seam, with good understanding that allows you to control them, so that you know when you frack, the fracture will not go outside of the shale seam, either up or down. That addresses a safety issue. And then you can make sure, if you control them well enough, that they cover the entire shale seam, so that the gas that flows from those fractures will be more than 15%, some bigger number. So that helps both sides. In the short term, that's probably not going to happen. If you want to do shale gas safely, you'll have to use regulation. And the states do the regulation at the moment, so there are 50 different approaches to this problem, potentially. But that regulation, which we need, could be replaced by better science and just better technology that comes from those science discoveries. So the science challenge is at the bottom: understand and control fissure mechanics, pore formation, and fluid flow in fractured rock. That's a science problem. So what about the next one? So carbon dioxide mineralization. So those are two that are on the road but not sustainable. We need to make them sustainable. Here's some ideas, not yet on the road, but maybe very good ideas. And over 50 years, you may be able to develop them. So what do you do with the carbon dioxide that's now produced by fossil fuel plants? The idea is catch it at the flue and put it underground, where you really don't know what will happen to it. So underground, it's at high pressure, usually high temperature because it's deep underground. It reacts with the rock formations there. And my geologist friends tell me there may be 12 or 15 different kinds of rock formations that it could react with. And it may migrate. So the underground rock formations are porous. That's why there's room for the carbon dioxide. But that also means it can migrate, and it might go to a place that you don't expect. It might even leak back to the atmosphere. And if it leaks back to the atmosphere at even a 1% rate, then everything you put underground in the first year has leaked out in 100 years, and 100 years is a short time in climate change terms. So you have to keep it underground much longer than that, maybe 1,000 years. So there's some issues there. So here's an alternative. Why don't you mineralize it? So I've shown a chemical reaction here, but let me first look at the upper right. Carbon, when it reacts with oxygen, produces carbon dioxide, which is very stable. You see a number, 394, never mind what the unit is. that tells you how stable it is. It's much more stable than carbon. And in fact, there are not many things that are more stable than carbon dioxide. But one of the things that's more stable is carbonate, like calcium carbon O3, that's calcium carbonate. It's even more stable than carbon dioxide. And the stability is illustrated here by the table below. So what am I showing there? How much carbon can you store in the atmosphere? This is a known number. It's about 720 gigatons. How much can you store in the shallow ocean? Well, it's not so different from what you can store in the atmosphere. And what happens, the dynamics of this, is the carbon dioxide comes out of the atmosphere, goes into the shallow ocean. That happens naturally. And through the ocean circulating currents, the so-called Great Ocean Conveyor Belt, which goes on the Atlantic Ocean, up the coast of the United States, and back down Europe, and it goes deep in Greenland. It dives deep. It goes deeply. Goes down to the deep ocean. That can hold a lot, 36,000 gigatons or 37,000, and that's the reservoir that everyone's counting on ultimately to capture and hold the carbon dioxide for a long time. Carbonate rocks just completely dominate the deep ocean. So 60 million gigatons. That's because they're so stable. And they're on the surface of the Earth, potentially. No reason to bury them. In fact, if you make buildings out of them, you see the buildings and get some benefit. So it's a very attractive solution compared to sequestration because, number one, it's stable. You know where it is. It's not going to go anywhere. You can watch it. It's on the surface of the Earth. You don't have to probe underneath. And its capacity is huge. The last line of that table is, what if we burned all the fossil fuels? How much carbon would we get? Well, 4 gigatons. So the carbonate rocks wouldn't even notice it. It's nothing. So here's a very attractive solution. Why don't we do it? Well, the reaction is rather slow. So you need to speed it up in some way. That means you want to find a catalyst for this reaction. But that's what we know how to do, right? We've been doing catalysis for 150 years. So potentially we can find a catalyst for this. And it's usually the surfaces are coated with a passivating layer. So you have to control the surface of the rocks that you're reacting. But again, we know how to do that. Surface chemistry and nanoscience are teaching us how to deal with surfaces. So we could do that. So that's something that we haven't really started seriously yet, but over the 50-year time scale looks very attractive, and we could. Let's talk a little bit about storage, coming back to your question. So here is the growth of electricity since the early days, 1880, as a percentage of our primary energy supply. So it wasn't much back in 1900. We used it mostly for lights. Then we started to do other things with it that you see here. And now it's about 40% of our primary energy. And it's a really wonderful energy carrier, as I'll show on the next slide. If we get electric transportation going, that's going to grow to an even bigger number. The potential is huge there. So we like electricity. It does all these things for us. This slide illustrates where we get our electricity and how we use it. So where we get is on the left side. The traditional mechanism is coal or gas combustion. Use that combustion to turn a turbine, so a heat engine. On the end of that turbine, put a generator which rotates and makes electricity with magnets and wires and so on. That electricity goes through the power grid, and it gets used on the other side of the power grid for everything that you see here, a host of uses, very, very versatile. You can see what they are, and at the top, electric vehicles, if they take off, will dramatically change that situation. You don't have to get it from burning coal or gas. So you can get it from nuclear fission. That also produces heat. You can get it from the sun, solar thermal. That's the yellow box above. So you don't use any combustion at all. You just get the heat from the sun, which you focus. You can get the mechanical motion without the heat. So wind or hydro turns a turbine with no combustion. You don't even need the mechanical motion. You can, from photovoltaics, get solar electricity directly from photons from the sun, turn it into electricity. So there's a lot of sources, some of which are quite renewable, and a lot of uses. And if you look at, so a lot of our electricity now comes from combustion. If you don't consider that, but everything farther downstream, it's clean, it's efficient, it's versatile, many sources and many uses, and it's really an energy carrier, a choice for the future. So that's something we would like to exploit. But there's one reason why we can't exploit it, and that is we don't know how to store electricity well. So in this system, you have to make it at exactly the same rate that you use it. So you balance the load and the generation. And that's a tough job, which we've learned how to do through engineering, clever engineering. But you'd like to store it and use it at a time when you need it. So here is a battery development challenge, and this is what JCESR is trying to do. Illustrated here by all of the energy uses in 2009. This comes from the EIA. You see the biggest single one is transportation at 29%. And there are three gray sectors, which are smaller than that, but add up to 40%. That's all the ways in which we use electricity. So 69%, nearly 70% of our energy goes into electricity and transportation. And each one of these sectors is waiting for a transformation. It's obvious what the transportation transformation is. That's replace foreign oil with domestic electricity. You need a better battery for the car to do that. In the case of the grid, we've already mentioned coal going to gas. That's being helped by EPA standards and also by cheap and abundant shale gas. But there's one more transformation, go to wind and solar. We mentioned earlier that sun only shines during the daytime, and even during the day, the clouds obscure it. Wind farms, every month, there's at least one day when it's calm. So if your electricity from wind and solar is, say, 30% of your supply, you should store it. If you don't store it, and what people do now for wind farms is build a gas turbine plant right next to the wind farm. And on the day per month when there's no wind, you fire up the gas turbine plant. That's the most economical way to back it up. Does that really make sense? So you're building twice the infrastructure you need for 1 or 2 days. You hardly use it. And the rest of the time, that gas turbine just simply sits there. Wouldn't you rather have a battery or store that energy, which actually can work continuously, 24/7, throughout the month to regulate the voltage or the frequency and provide other services to the grid, which the gas turbine, when it's off, simply doesn't. So this is the opportunity. The bottleneck for both of these transitions is cheap, high-performance energy storage, and that's what JCESR wants to do. So this slide illustrates, there's a lot on here, but I'll just summarize it. Never mind the left. If you like the numbers, you can take a look. The vision of JCESR is to transform transportation and the electricity grid with high-performance, low-cost energy storage. We have a mission, which is captured in the phrase 555. It means 5 times the energy density, 1/5 the cost, do it within 5 years. Those are the 3 5s. And that's a very aspirational and visionary mission, but within the realm of possibility, and I'll talk about that in a minute. We'd like to do this, leave 3 legacies. So we want to leave a library of fundamental knowledge about energy storage. By the way, you won't be able to get these factors of 5 with lithium ion. So that's a phenomenal energy storage that powers our cell phones, but it gets better at about 5% per year in energy density, and its cost goes down at about 8% per year. These are quite important numbers. Yes?
What about mechanical batteries as opposed to chemical batteries?
Yeah, that's an opportunity, and lots of people are looking at that. And I saw an interesting proposal to simply lift rock a few hundred meters instead of water and let it come back down. And that's an interesting idea. I don't know what the cost of that is or what the technology is. I'm sorry? Yes, it's like hydro, it's like pumped hydro. Yeah. It's a great technology. There's only 2 restrictions on it. You have to have water and you need a mountain. And that doesn't apply everywhere. But this idea to artificially create a cavern where you lift rock up and down is sort of the flat analog of that. But yeah, that's an idea. Yeah.
What about superconductors? Has there been any effort to
Yes, there is.
push that as a energy storage?
So that's a great idea. Superconductors in magnetic fields. So SMES, as it's called, superconducting magnetic energy storage, where you drive a current through a magnet and the magnetic field comes up that takes energy, which goes like h squared. So it gets better with scale. And it's still too expensive, but that's an idea that should be out there. So the way I'm thinking, and I'm proposing that we all think, is what are the opportunities going forward, not what are the restrictions on the technologies we have now. And that's one we should be looking at too, absolutely. So we're looking at batteries. We want to do the fundamental science. We want to get the 2 prototypes, one for transportation, one for the grid, that meet these 555 goals. And very importantly, the last one, a new paradigm for battery R&D. So we want to combine discovery science, battery design, research prototyping, and manufacturing collaboration. We're not going to manufacture, but we'll talk to those folks, all in one highly interactive organization that, in the battery field at least, that's never been done. And it's this paradigm that may enable this aggressive mission goal of 555, this new paradigm. Pardon? Antitrust, in the sense of... Oh, good point. So, yeah, we have 14 partners in this consortium, 5 national labs, 5 universities, and 4 companies. The only one that's a battery manufacturer is Johnson Controls, or JCI. They make lead-acid batteries, and it isn't clear that they'll be the recipient of the technology we develop. They may be, of course, but it will be available to anyone. So that's a good point. Yes? Absolutely. So if you think about organic molecules, what's good about them? First, they're cheap. So it's carbon, hydrogen, oxygen, nitrogen, typically. And those are all earth abundant in their elemental form anyway. They're completely harmless to the environment. You can recycle them. And these are all good things. Another good thing about them is you can tailor them. They have complex structures. So you can control the structure, which then controls the properties. So with a simple basic quinoxylene, but never mind what it is, structure, a base, you can hang ligands on it that change the solubility, that change the electrochemical activity, and so on. More or less it will. So I think it's a huge opportunity. In fact, JCESR is exploring that. So that's a very good point. Was there another question? Yeah.
For the 2 batteries that I know about, the lithium-ion and the metal air,
Right.
metal sulfur, and the redox
Yes.
battery station, is that going to be the 2 target systems at JCESR, or are you guys looking beyond that?
Great question, and thanks for asking that. So we have to look beyond lithium-ion, and the 2 you mentioned, and there are others, lithium air is one of them, lithium sulfur and redox flow, are beyond lithium-ion. They're fair game for us. But we think of these as concepts. So instead of saying we're going to develop a lithium air battery, actually we don't say that. We're saying in our first legacy, we want to understand how the lithium air battery works. And once we understand how it works, that'll be true for other chemical, it doesn't have to be lithium and doesn't have to be oxygen, other chemical reaction batteries. We'll look for the one that is the best. And we have another concept, redox flow. We would also like to replace lithium, which has 1 charge, with magnesium, 2 charges, or aluminum, 3 charges, and thereby double or triple the energy density in a single stroke. But these are 3 concepts, and we expect that the battery we produce will draw from all 3. So we're not trying to make 3 batteries. We'd like to make 20 batteries, combining all of these concepts in various ways. Great question. Thank you. Was there one more?
What about advances
Ah,
nanoscale?
right.
Is that, are you investigating that in terms of just build structure, tiny structures, increase density?
So that's, just to repeat that, 3D printing, I think was what you asked. Yeah, and in fact, we have one of our scientists and her team are looking precisely at 3D printing and whether you can make batteries out of 3D printing. So you save a lot of material, right, because you only make the components that are active that you need, and the rest stays on the table.
And it says that if you can do the really tiny scale, you can do that interaction.
Absolutely. So that's, and we are looking at it. It's a great idea. And there was one more question, I thought. Yeah. Oh, sure. At the moment, it's thought not to really have the capacity to serve, a big fraction of our needs, but it's still being looked at. And this is an example, I think, of an innovation that we need to understand better. So you can do an ocean current, you can do the tide going in and coming out. That's an opportunity to generate electricity. All of these things are there. They don't really store. So when you look at ocean currents, they produce. And they may be pretty constant producers, so that's great. But they don't really store. You still need a way to store that electricity if you're going to cut out these peaks and valleys that we just have. Yes?
Is this the sole mission of the Joint Center that's on the screen, or is it one of a number
No,
of missions?
that's the sole mission. We won't do anything else.
Well, then it seems to me that that's kind of narrow in the 50-year future
Absolutely.
timeframe that you spent most of your time talking.
You're absolutely right. And the reason that it's this narrow is that there's not enough money in our contract to do more. So if you're going to be effective, you have to focus, and we'll leave that to some other group. But yeah, there are other ideas too, sure. So, yes.
We have a question that came in over Twitter.
Yes.
From Intelligent Event. They asked, is there a future for thorium in the nuclear
Oh,
energy?
that's a great question. And okay, let's go back to that. Maybe we can. I really like that question. So here's. So this question was, is there a future for thorium in nuclear reactors? So thorium has a lot of advantages. It's pretty hard to make a bomb out of it. So you think you're pretty safe from terrorists and rogue countries. There is a lot of thorium in the world, so you can mine it. There are ways to reprocess the fuel, not the same as uranium, but you can use it over and over again. We, the United States and most of the developed countries, didn't decide to do that back in the 1960s. And if you read the literature, you see the opinion expressed that the reason we didn't do it is back in those days, we wanted to make bombs, and we wanted to develop uranium technology because you could also make bombs from it. Nowadays, we don't like bombs, and most of the world says, let's get rid of them. And if we were back in the 1960s now, or if we're making our nuclear decisions now, we might make the decision to use thorium. But we have so much momentum built up with uranium reactors that it's difficult to break that pattern, although India wants to break it. And they are blessed with lots of thorium ore, and their plan, at least, is to develop the thorium reactor for use in India. But that's a great question. So let's skip forward. I had one more challenge, and this is the farthest one outside the box. But again, thinking of the 50-year time scale, it may be within reach. And that is develop chemical fuel as a sustainable energy carrier. So I'm going to tell this story chronologically. Go back to about 2003. And that's when President Bush at that time said hydrogen. And he said, for example, a baby born today will drive, the first car that baby drives will be a hydrogen car. So 16 or 18 years. A very visionary statement. And the idea of how that works is the upper left diagram. So you burn the hydrogen in your car. It produces water, H2O. That's the only combustion product. That water flows back through the environment some way and would get split by either solar energy, solar electricity, electrolysis, or wind electricity, somehow a renewable electricity source, back to hydrogen, and you would just simply keep recycling that for a long time. So it's a wonderful idea, actually. But people realized after a few years that's pretty far off. There are a couple of breakthroughs that you need to get that we don't have. It might still be within the 50-year time scale, but it's a little too far off to bet on for the near future. So the next idea that came along was, well, let's use biofuel. And in 2007, we started, there were lots of bioenergy research centers were funded. So this research is still going on. And the idea is burn a hydrocarbon, not just hydrogen, but a hydrocarbon. It's got some carbon in it. And the combustion product is carbon dioxide and water, not just water. The water would go back through the environment and then through a plant. You'd use biology to combine the water, that's the combustion product, and the CO2, which is a combustion product, and produce things that could be turned into fuel. So you don't want to do it with corn ethanol because we didn't realize initially, some of us did, but now we all realize that that has about the same carbon footprint as gasoline. It's a little better, but it's not a lot better. So do it with cellulosic ethanol or other so take the cellulose of the plant, much better deal energetically. And it's, again, the sun that makes the plant grow, the photosynthesis, and regenerates the used carbon dioxide and water back into fuel, which requires some processing. So a challenge with this is that even the most optimistic estimates of how much transportation fuel you could produce by this technique it's 30%. So that's great. You solve 30% of the problem, but you won't solve 100% of the problem. So maybe you could do better. And the last thing here is the doing better, and that is forget the biology. Don't use the plant, but just use artificial materials and chemical reactions in the laboratory to reconstitute, reform the carbon dioxide and the water from combustion into a fuel. So, and if you look on the next slide, so just to dwell on this for a minute, you would keep using the same fuel over and over again, burning it to produce carbon dioxide and water, reforming that in the same amounts to produce the fuel, and keep doing it. You don't add any carbon dioxide to the atmosphere. That's the vision. And on this slide is shown all the ways you can accomplish this process. So if we go back one slide, there's one way or a few ways, whatever biology gives us in the middle diagram. There are many, many more ways in the lower diagram. So if you don't depend on biology, there's lots of routes. Never mind what's on this slide. It's too detailed. It's an eye chart. But it's supposed to illustrate that there are lots of ways to do it. So one or two may not work. Maybe another one will. There's a lot of research to do here. So it's farther out, but it's receiving some attention, and it's really a wonderful goal. Think of making chemical fuel sustainable, then that solves a problem. So if you want to solve that problem, you got to do some science and get some breakthroughs. So I want to now end with a very important point, and this is kind of fundamental. The cost of doing things. Yes?
Quick question. The one thing that seems to be missing is the category of conservation and efficiency.
Yes.
Existing system.
Completely agree with you.
Point out most thermal plants which generate electricity are most a third efficient.
Right.
Those cooling towers are giant radiators.
Right. Waste heat. Yeah, absolutely. So if you ask this question, what's the biggest source of additional energy that we could get right now? It's certainly conservation and efficiency. If we just use less energy, that's energy we don't have to make. And that's the biggest opportunity in the near term. And we should be doing that. I completely support all that. In the longer, I mean, you probably won't get all the gains you need or would like to have from that. And that's where these additional technologies would come from. But I fully agree, you need that. So the cost of doing things. So rule of thumb, and most people agree with this, that if it cost you $10 to discover something, that's the little box there on the left, it's going to cost you 10 times that amount, so $100, to demonstrate that it can be a technology. And it's going to cost you another factor of $10,000 to commercialize that technology and deploy it. So where does that money come from? Well, the discovery money, actually, the government has enough money to do that, and it funds most of the discovery science that we do in this country. It does have enough money to do that. It doesn't have enough money to demonstrate. That takes an industry company somewhere, or several companies that work together, to show that this could work, kind of on a small scale, and that's an industrial challenge. Nobody has enough money to actually deploy, no company. The only people who have enough money to deploy are us consumers. So if you think of your cell phone, we love cell phones, and we're willing to pay hundreds of dollars for them. And it's us that are paying the bill for that deployment and the future development of those cell phones. So somebody has to take a chance and say, I think this is going to pay off big. And indeed, if it does, they get rich, like some of the digital companies. I'll come to you in a sec. But that's where the real rubber hits the road. So the point I want to make is that even in tough times, like now, when money, government money is hard to come by, we ought to invest in discovery, because that's the seed corn for the future. So you don't have to develop it now. You can develop it 5 years from now when maybe times are better, or 10 years from now. But you shouldn't give up on that. It's relatively cheap. Yes?
Take that chance. You really need incentivizing the innovator, and he's not going to be incentivized unless the reward for the risk is going to be really high.
Right.
And one of the most significant potential problems that I see as a business person is the complete lack of protection for IP on a global scale.
Good point. So go to some Asian countries that shall remain nameless, and you really can't. You don't know that your IP is safe. And there's many examples to prove that. So, and that that IP system, at least in this country, was developed in revolutionary times. Before 1800s. Of course, it's been upgraded, but it's not really adequate, and I completely agree. I don't know what to do about that, but that's a problem. Yeah.
One question that comes to my mind is, you solve all these energy problems, and energy price goes down in the most optimistic scenarios. What stops us from just having a lot more babies and having more people? I mean, isn't that what happened in the late 1800s?
Sure.
We figured out how to synthesize ammonia?
Yep. And we solved the problem by the so-called green revolution. How do you feed all these people? First, we had the fossil fuel, which kind of made us able to support more. We got more, and we decided, how do we feed them? And we had the green revolution. That's kind of done. So how are we going to feed them? And there's lots of questions as population goes up. That is a wonderful question. I wish somebody could answer it. Yes.
Actually, the figures show that population growth has ended.
I would like to see that, actually.
It's way down. Birth rates in developed countries are way down. Birth rates in developing countries are way down, higher pace. So,
Yeah, and China.
The secret, the answer is unpleasant but doable. It requires educating women.
Yes, and cultures.
Educated women, they don't want to have sex babies. They want to have one or two.
So that's a good point. Another question.
Depends on your point of view.
You were
Yes.
talking a lot about kind of meeting increasing energy demand. So what role do you think, or what impact do you think is actually going to have the real conservation of energy?
Yes.
So using the energy that we have a little bit more smarter than we currently do. Do you think that's going to have any impact, play a role?
Well, so it's hard to know what will actually happen, but you can compare the U.S. with either Europe or Japan, which uses about half the energy per capita that the U.S. uses. And that kind of tells you that it is possible to make a factor of 2 difference and not suffer much, still have a technological life or society. So there could be a huge impact there. How do you make that happen? In this country, at least in many developed countries, we like to have choice. So I'm going to do what I want to do, and if I would like to drive an SUV all alone, I will. Something has to kind of change that. Most people say it's economics, but there could be just a sudden epiphany in enough people that, hey, we shouldn't do that. Denmark has done it. I'll take one example from Europe, by raising the price enormously. So if you want to buy a new car in Denmark, you certainly can, but the tax on it is 100%. And so most people decide, maybe I won't do that. And good point. Yes?
Your last slide here brings to mind a question referring to earlier your discussion about wind and solar. And again, in your 50-year time frame, how do you justify the major subsidies today that are being injected into wind and solar? Not into research, not into development, but into production.
So let me go back a few slides, because there's a very interesting thing that you probably didn't notice on this slide, which is very relevant to your point. If you look at the wind here, you see 3 plateaus around 2000 and the years following. What do you think caused those plateaus? What do you think caused those plateaus in the rate of growth of deployment of wind? Yeah, it was the incentive was removed. The production tax credit expired, and it took Congress a year to renew it. And when they renewed it, you see that suddenly there was an uptick. So,
but is it not a house of cards? We're not going to subsidize wind and solar forever.
Right. Let me be controversial and say that in the case of fossil, we've subsidized it for a long time.
Yeah. Continuous, so.
Yeah.
How have we subsidized? As nuclear and everything. That's not true. No, not true. How are we going to reach the Iran? Most paying countries pay billions of dollars in taxes. We pay for the building of the plant before they have.
So that's a good point. And I would love to get into the discussion. Let's do it in a couple of minutes. I've got one more slide here that I'd like to show. But that's a good point. So let's jump forward. I think I made my point that it's a good idea for societies to invest in deployment, in discovery science. And this, in fact, is a slide that just says what I said. I'll add one thing. You can read that if you like, but I'll just add one point, that most economists will tell you that half of the GDP growth since World War II was due to innovation. And innovation is based, to a large extent, on discovery, give you something to innovate on. So it really pays off. So when you invest in discovery, the returns are much bigger than the investment that you make. And indeed, it's your seed corn for the future. So I wanted to end with this. Andrea mentioned, and at the beginning, this bookends the talk. We have this Summer Institute on Sustainability and Energy. I gave this very talk at SEIS this year, and it produced a lot of discussion among these graduate students. And that's the kind of critical thinking. I don't say I have all the right answers, but I can make the students think, and I hope I'm making you think, that we need to think about our energy future in ways that we didn't think previously. If anyone's interested, there's a website there. We'll be having it again next summer, and love to take your application. So with that, I'll end. Thanks so much. I see a hand over here. Yes.
We have mobilized and personalized all of the things that we use today. I mean, why don't we personally, or why don't we produce power locally? Why do we have to keep it centralized and a few people controlling who gets what?
Yeah.
I'm not trying to say that you've got to distribute it well. What I'm saying is, if you have it locally, you cut down on various losses like transmission, etc., and you you can actually control how much energy you want instead of storing it somewhere else. And the storage cost is completely gone if you produce it locally. Why don't we do it?
So that's a good question. I'll give you an example of what could happen. Well, I'll give you an example of what did happen to telephones. So we used to have landlines, and you had a phone in your home. If you wanted a phone, you got the phone, and that's no choice. You can have the phone or not. That's the only choice you have. Now with our cell phones, we actually don't need the landlines. And you can personalize your phone to do lots of stuff for you. And from the sales of iPhones and other phones, it's clear that we love the cell phone. So could that happen in the electricity business? Well, you could put a solar panel on your roof. You could put a battery in your basement. They're both DC, so you could charge the battery from the solar panel when there was excess sun. You could use the electricity from the battery whenever you want. Most of the things you do in your house could be run off DC. In fact, your cell phone and your computer are DC units. The first thing you do when the AC electricity comes in is convert it to DC. And that means you could locally produce a lot of the electricity that you need. And that electricity would be, in principle, or could be, independent of the grid. So do you really need those grid landlines to supply you? Well, you'll never get away with never having them, but maybe 60% of your energy use or 80% could come locally, and you just control it yourself. The battery, of course, would do much more than store the solar electricity. It could help to regulate voltage and current and improve the quality of power. It could also be a backup in case a tree hits the power line or Hurricane Sandy comes back. Then you'd have a local supply of electricity for yourself. Think about that model in the case of a commercial building or a neighborhood. So you might have a microgrid that serves a neighborhood with its own storage bigger than what you'd have in your basement, but sized to the needs of the neighborhood, and also providing many more services than just simply storing the excess electricity. And this is a model that people are starting to take seriously. So it's a wonderful question. Yes?
Quick comment on the discovery science payback.
Yes.
If you look at what happened with Google, I think it's getting paid back with the entire research that was done in Stanford. And now it is getting paid back in terms of whatever Google is returning to you as a service, as well as taxes to the government. No question about that. And that is very, very typical of almost every discovery science. The government gets into it and it really multiplies and remultiplies in many, many ways. No question about that. And that's probably where the subsidies are worth. You've got to look at them as investments for underserved areas rather than giveaways to these organizations. All they're really trying to do is encourage them to taking some more additional risks in their ventures and entrepreneurship.
Good point. And is there an answer to that?
Between investment in research and investment in production. You can't lump it all together as a justifiable investment. What the government has invested in certain areas of technology is in research, and rightfully so. And I think that's one of the messages.
That's the message, right?
Strong message of our discussion tonight. I'm talking about production, that the consumer is reduced the cost of buying electricity at the government subsidy. I don't get it.
So here's a comment. Here's a comment on that. The typical incentive that we have now is based on if you make, I'll make it cheaper. Let's take wind. I'll give you an incentive, the government does. So it's cheaper for you to deploy wind, and you'll learn after 10 years of that experience how to make the cost even lower, the typical learning curve, and eventually I can take that subsidy away. I would like to actually propose a different kind of subsidy. A subsidy that's an incentive to make the technology better. You only get the subsidy if you make an improvement in efficiency or take your metric, whatever it is, but not simply just number of units sold. And I think that's a different way of thinking about things that would, to some extent, address some of the issues. So that's an argument that we probably won't settle tonight. But I like the discussion, and if I can just add another footnote to that, take it's in a sense oil, because we built in the 1950s the interstates, and the government paid 90% of the cost of the interstate. Who benefited? All of us, because we can now drive on vacation or wherever we like. The freight companies benefited. We've got roads that, you move stuff. And the military benefited, and in the 50s, that was one of the justifications that we can move missiles around or whatever else we need to move around. So there's a government subsidy of a lot of things. The oil companies benefited because we all bought cars. But it really helped society enormously. And if you can find those kinds of subsidies that actually have a broad impact, help us all and help society, those are in a different category, I feel. So just a comment. Yes?
We got another question on Twitter. What work is being done on capacitors as potential energy storage?
So I was talking about JCESR being limited to beyond lithium-ion batteries, capacitors, supercapacitors, and electrochemical capacitors. That's another opportunity that actually is very ripe. There's lots of research going on and that could be done. Capacitors have a fast response time. They can be rather high capacity, and you may want to combine them with the battery because the battery can store for a long time. The capacitor can respond basically instantly in milliseconds. So I think it's a ripe opportunity, and there is actually a lot going on. JCESR is not doing it, but it's a great question. Another question, and back here, and then we'll get everybody. Yeah. For the carbon capture, I didn't point it out, but you noticed it. It's actually a downhill reaction. So it happens spontaneously that carbon dioxide will react with a metal oxide to make a carbonate. And energy's coming out. So you gain energy by that. It's not a lot compared to how much you gain from, say, burning carbon, and that was on the slide, that was 394. Not at all. It happens automatically. It's thermodynamically favored. But it goes really slow. Pardon? Let me go back to that slide. There's a lot of them. So, let's see. Oh, I went by it. Here it is. So there's the chemical reactions. So any metal oxide, M is any metal, plus carbon dioxide goes to the carbonate, the same metal, it's a carbonate, and energy comes out. That's the basic equation. One that people talk about a lot is magnesium silicide beneath it. So that reacts with carbon dioxide to make the magnesium carbonate and some silicon dioxide, basically just sand, and energy comes out.
You have to worry about the decomposition reactions. This is something that is not applicable to Earth.
So, good point. So, in all the history of the Earth, and it's been hot and cold, these things have been so stable. Look at the amount of carbonate rock. So, if they were unstable or if they got too hot and they decomposed, those guys would go away. And at least the evidence up till now is the Earth isn't that warm. So as long as we don't get too warm, we're fine. I don't know where the limit is. It'd be interesting to look at Venus and see where the limit is.
We have to establish robustly those limits before we get this up to ensure that reverse process doesn't.
Yeah, absolutely. I think it's pretty easy to do that, and I don't know the answer, but yes, that question should be asked. And my guess is that we're okay, but we should ask that question and verify it. Absolutely. Yes, and then we'll come back here.
You mentioned that with thorium-based nuclear energy, that would be a substantive value, especially for geopolitical stability, in the sense that nuclear non-proliferation component of it. And the other one we have not discussed in this presentation is geothermal.
Yes. And geothermal, I mean, at UIC, which is my home institution, there are 3 buildings that are heated exclusively by geothermal. That's about, I don't know, 5 years old now, and I'll tell you this just number. They save 40% of their heating and cooling costs because they take the heat out of the ground. They use the energy in the ground. And to me, that's a no-brainer. I don't know why people do that. It should be on my list of wind and solar. Let's just keep going. Absolutely. Question over here. Yes? Yeah, so there's lots. There's lots, yeah, precisely, and there's lots of ways. Geothermal means lots of things to different people. What happens at UIC is actually shallow geothermal. It goes down 500 feet, and they use the constant temperature down there as the base. So in wintertime, you don't heat much. I'm sorry? Yep, okay, I completely agree with you. That's right. Yeah. Question here.
The chart here shows deep ocean capacity of about 37,000 gigatons of carbon.
Right.
What if you used a large fraction of that? What are the implications for ocean acidification?
Well, you will certainly get acidification. And that's an issue that I'm not sure we understand where that's going. So if you said, let's burn all the fossil fuel, which is the bottom line, and put all those 4 gigatons in, so use 4 of the 36 for the new fossil CO2, what would happen? There'd be a lot of acidification in shallow and deep, and that's harmful to ocean life. I think that's the problem. And I'm not sure we actually understand what that would do. Yeah, good point. Yes?
I was thinking of that as because you feed it to clams, they'll make more clam shells.
Sure.
That would just solve the problem. A wild question. Wind farms work by taking energy out of the atmosphere.
Right.
How much can you take out of the atmosphere before the climate
starts to change? Yeah.
By the lack of energy, by the change of energy in the atmosphere.
So there is Keith, I've forgotten his first name, anyway, from Canada, who just moved to Harvard, who looked at that question rather in detail. And he concluded, and others have too, that, yeah, you could do that, but at the energy scale that we humans require, anything that we would do, I mean, short of 100%, I'm sure, but even 100%, would have a negligible effect on the climate. I'm not sure that one should believe that, because there's lots of unintended consequences, in everything we do, and I'll give you an example. 50 years ago, we thought the atmosphere is infinite. Let's put our CO2 up there. Who cares? It's not going to do anything. And some of you, I'm sure, know this. This is a savvy audience. The amount of CO2 in the atmosphere is 400 parts per million, so far less than 0.1%, almost nothing. And yet, it's enough to have a huge unintended consequence. So when you start to ask what would happen if you extrapolate, say, ocean acidification or other things to big numbers, I'm not sure we really understand that. Good point. Yes? I don't know the exact number. It's not a big fraction. So there's much more going into the other things some of the other things that we've discussed here. So it was taken seriously 20 years ago, maybe it's 30 years ago now, where we would dig holes, and I'll tell you the story about geothermal, not the kind for heating in winter and cooling in summer, but just getting energy out of the ground. If you dig way down, you find hot rocks. Thermal plants. Pardon? Yeah, precisely. And then you would put cold water down, the hot rocks would heat it up, the hot would come up as steam, and you'd turn a turbine with it. Yeah. And that works great. And they found that after some number of years, like 5 or 10, they quit working. And what happened was all the heat locally of those hot rocks was taken out, and not replenished by being, by coming in from the surroundings deep in the ground, you have to stop producing the heat that way, stop putting the cold water down, and after 10 or 20 years, it regenerates. So it becomes hot again. So it's cyclical, and it's not a continuous source. So this is now referred to as thermal mining. So you take out the heat that you can take out, and you have to wait a while for the heat to regenerate it in the deep underground, and you can take it out again. That apparently is a very big resource, as opposed to the amount you can take out continuously, which is much less. But it's a good point. Yes?
I think one way to get development money, redeployment money, is to change the stock trading incentives from how many transactions you make, transactions related to, say, technology, research, and development. So right now, anyone could do it. I mean, if we really want to raise the money to start the third phase of the process after you get through the research and the development, you want to deploy it. But I think the trouble is you need grown-ups and you go Wall Street and your political arena before you can get any of these programs working in the people. Because we don't have anybody like a Miss Merkel in the United States
To actually control it. So good point. There's lots of special interests around. Many of them simply want to make money in the short term. Yeah, that's a problem we need to work with. You had a comment.
You described batteries as a way to substitute for renewables when they're off for a day.
Right.
Do you foresee this next generation of batteries being better for some reason for single large utility scale installations rather than maybe a network of smaller used in cars or some other distributed system?
So it's an argument that's going, or discussion that's going on now. Do you want to store centrally, say next to the wind farm, or do you want to store locally, and they have a phrase for this, at the edge of the grid? It means a house or a little neighborhood. And the opinion now is trending toward, let's distribute the storage at the edge of the grid and do it either at the single residence scale or the neighborhood scale or the commercial building scale. And I think there are a lot of good reasons for that you can get a lot more out of your storage. It can do double or triple duty if it's tailored to the local needs, whereas if it's next to a wind farm, it basically can only do one thing. So that's the way people are starting to think.
You can also produce thermal storage from wind and solar, and then spin a turbine with that.
Yeah.
That same, thermal molten sulfur, whatever the heck you use for heat transfer mechanism, and do that later.
Absolutely. So you can.
There are multiple approaches to
Right.
the issue.
This is what makes it so.
Storage is the question. There are many ways to get there.
That's what makes it so interesting. So intellectually and for critical thinking, which one is the best, and what you might conclude now might be different in 20 years, just because the energy landscape is different. So that's a good point. I agree. Yes, and then back there.
I think there are a number of good reasons why the energy economy should decarbonize in the long term. I mean, you mentioned climate change as one of those reasons, but not the only reason.
Right.
Well, do you believe that the strategy for the future should have a long-range portion committed to adaptation? Because if we bet on climate change and do the things that we suggest and we're wrong,
We're stuck.
then it's too late.
Yep. So my opinion is a tiny voice, and I'm not even sure. I may change my mind in 5 years, but I think you have to do both. So I think it's cheaper to prevent than it is to accommodate. So if you can do that, you should. A lot of people say now that we're already getting climate change and we should be accommodating now. The city of Chicago, for example, plants trees that can thrive in warmer temperatures, anticipating that over the life of the tree, it's going to be warmer. So that's a common sense thing that you would do if you wanted to accommodate. And there probably are many things like that. What's the balance? Boy, that's a tough question.
Well, my own observation is we're doing virtually nothing.
For accommodation.
To adapt.
Yeah, to adapt. Yeah.
And,
Right.
and I think that's just not the right strategy.
Good point. I like that. Yes.
So
Yeah.
Like, do you think as a person more SBIR, or I don't know, do you have any opinion on this?
So we didn't talk about entrepreneurship, but I think it actually is very important. And one reason is that most of the things we've talked about, electric cars are a good example, are not easily taken up by big companies. So they are pretty happy doing what they're doing. Why should they change? They don't want to take a risk. And it takes a risk in order to get some of these innovations started. So Tesla is a good example of a car company that is completely innovative. In many cases, the exact opposite of Detroit. That's an overstatement, but they just don't think the way Detroit thinks. And they were given very little chance of success until their stock started to come up, and they put out the S-Car, which everyone loves. And they've shown that indeed it can work. So although that's not a mass-produced car and is not going to transform, probably, it does show that you can do it. And that's the kind of innovation you need. So how do you get that? I don't know. I think you do need to incentivize that. So SBIR is one way, but there may be other ways too. But I believe entrepreneurship is really important. Okay, 2 more questions. Good. Yes?
I feel like we're running down the road and ignoring some basic assumptions that are in error. And the first one is sustainability. And that several years ago we heard a lecture by Dr. E.O. Wilson, who's a world-renowned biologist.
Yes.
And stated that if all of the people in the world were brought up to the standard of living that we enjoy in the United States, that we would need the resources of 8 Earths.
Yes.
And in fact, the Green Revolution didn't solve a whole lot.
Right.
I just did my handy-dandy, I'm old-fashioned, I do multiplication by hand. And at an underestimate, the time in this that we spent in this room, over 12,000 people have died of hunger or starvation.
Yeah, amazing.
So this has not solved the food problem, and with increase in population, it's going to get worse. Right. And the projections are that the world population is going to be increasing to 10 billion. So all of this stuff doesn't mean a whole lot under those circumstances. Our standard of living may not suffer so much, and it may actually suffer a great deal depending on what happens. But we're very short-sighted when we look and just do things just for here.
So just to cast that, to amplify your comment, what I presented was that you have to have economic growth if you want to go forward. And I think what you're saying, and I agree with this, is that ultimately that has to fail because the Earth is finite, it has a certain amount of resources, and you'll eventually grow to the point where you can't do that anymore. So I don't know what the answer to that is. You'd like to find a way that society can continue to improve and quality of life can go up, and it doesn't require using more resources, and we won't eventually hit the limit. But what you raise is an absolutely fundamental point, and I don't know the answer to it. I think it's a really good question. One more question, and your hand is up. Yes.
How optimistic are you that we can make this transition? While we were talking here, I noticed that one technology we didn't bring up, and I'm sure it's because it's been such a difficult problem to solve, is nuclear fusion.
Yeah.
Right. And some technological problems, it's just too hard to get there. And how optimistic are you that we can solve the trap, we can solve nuclear fusion?
So I think there are lots of options. We talked about some of them here. Fusion's one we didn't talk about, and there are others. That there's no shortage of ideas and potential out there. We do have to give up on things, and let's see what happens to fission. I mean, there is an argument right now. Switzerland and Germany say not going to do it anymore. We'll shut them down when their life is over, and that could die off. And fusion kind of never got started. We thought hydrogen was a great idea. We don't think that anymore. It's not for near term. So, but I think there are lots of opportunities out there, and I'm actually a believer in ingenuity and thinking, and I think we can do that. There's nothing that says we can't do it, And as long as we have the chance to be optimistic, I think we should be. So on that note, let's end. Thanks for the great discussion, really.